So, Bismillah ar-Rahman ar-Rahim. So at the beginning, I'll give a brief introduction about the topic that we'll cover today. So basically, the last section in that chapter talks about how to move data across the network. So there are some issues that we need to discuss in this part. So the first one is segmentation and multiplexing. So at the beginning, segmentation is dividing the long message that is coming from the application into smaller messages. So we divide the message into smaller ones. What is the purpose of this? It's to facilitate efficient communication. Why? For example, if we need to provide reliability, okay? If we have a large zip file, and we're moving this large zip file as one unit over the network. So imagine if one bit in that file is wrong, what we will have to do? So we will have to retransmit the whole file again as one unit. Versus if we do segmentation, we divide this whole zip file into smaller segments. So if one of the segments has any mistakes or it's totally lost, the only thing we need to do is just to retransmit this segment only. So we transmit smaller segment as opposed to retransmitting the whole file again and again. So that's more efficient. The other thing is that in a way we don't have a choice, because in some cases segmentation must be done because there is a limit on the physical medium for how large the information we're sending should be, right? So we cannot send over مثلا wireless, we cannot send one unit that's مثلا 10 megabytes. We cannot do that. So we have to break this down into smaller bits. The third thing that forces us to do segmentation is the fact that when we have smaller segments, we can facilitate the sharing of the medium between multiple users in a fair way. Because if we are sending one large unit of data from one user, all the other users will be waiting for the transmission of that user to finish. So that user, it's like that user is consuming the whole resources of the network, right? And all the other users are starving. They are hungry to use the resources of the network, but they have to wait, okay? So segmentation is a must. There is a slight overhead there is a cost that we have to pay. Because if we divide the original message into smaller messages, then we have to have some overhead to be able to recover the original message, the big message, from the smaller ones, which means that the segments have to be ordered and we have to put some sequence. If I divide a big message into smaller messages, so I have to say the first segment is segment 0, segment 1, segment 2. So I have to put some overhead in each segment that allows me to recover the original message from these smaller segments at the receiver side. So there is a big advantage for segmentation, but there is a slight overhead that we have to pay. So this is the first part. The second part talks about encapsulation and decapsulation. And as we said before, encapsulation and decapsulation happens in each and every layer. Okay? And the encapsulation in each layer has a different name, which we call it protocol data unit. So the protocol data unit for the application is data, for transport is segment, for the network is packet, for the network access layer is frame, right? So encapsulation talks about the process of enclosing the header specific to that layer, enclosing the header to the actual data that corresponds to that layer. So, for example, in the transport layer, the TCP protocol will add a header to the data, and then we'll send it down. And then the network layer protocol, for example, IP, will have to enclose another header to the actual data and send it down, and so on. This is the process of encapsulation. The reverse operation is decapsulation, is that you have a parcel, a box, and this box tells you how to open that box and get the package inside. So you open that box, you get the package inside, you find that this package has another box. You keep opening these boxes until you get to the actual data or the actual package, right? So that's the process of decapsulation. The last part.
What do you call the protocol after segments and packets?
segments into packets, that turns segments into packets. This is encapsulation, and this happens from the transport layer protocol to the network layer protocol. The IP protocol will enclose the IP header in the data coming from the transport layer.
So the protocol is IP.
IP, yes. Okay, the last part talks about how to communicate with another host on the same LAN or a remote LAN. So basically, in order to communicate with a host, you need to know two types of addresses. You need to know the physical address and the logical address. And as we said before, the physical address is like the name of that person. It never changes. It should never change, right? And it gives you an indication about the identity of that person. Okay? The logical address on the other side indicates the location of that person. So it gives us some information about how to send something to that person. So while we are in the university, for example, we have a specific logical address that tells people how to reach us, okay, in case they want to communicate with us. When we get home, we might have a different IP address which tells people how to really communicate with us while we are at home, right? So the logical address has a location significance, right? Versus the physical address is the identity of that person. And in case of communicating with a host, we need to know a logical and a physical address, both, okay? So the question now is that there are two cases. If we need to communicate with a person in the same local area network, it's like, imagine that we are in that class, and I need to communicate with a person who is in that class, okay? So in that case, I use the name of the person directly. I don't need to go anywhere else. I need to use the physical address and target that person directly, okay? Because he exists in the same class. If I need to deliver any like mail or something or a letter to that person, I will just go and hand it to him, okay? If that person is a remote person, he or she is in another location, in that case, I need to use some direction and routing, okay? Use, for example, like a mail service, like Qatar Mail or something, and hand the letter to them and ask them to deliver this to a specific logical address. Okay? So in that case, I don't need to use the physical address of that person directly. I need to get to the physical address of the mail service that will take this and deliver it to that person. So there are two cases here, right? So if we are communicating with someone on the same LAN, then we use his name directly. If we are communicating with someone on a remote LAN, we don't need the physical address of that person. We need the physical address of the router that will take this packet and deliver it to that person. Okay? So that's what we need to talk about today, and for that we have a set of activities. The first one is,
how will the router know the exact device most of the time?
The router knows that through a process of routing. That's in the network layer, and it uses like a lookup table, and we will talk about the details of this, how this routing table get formed, and how does the router learn about all these routes and stuff like that. We will talk about that. So the first activity is divided into two parts, and it talks about multiplexing and segmentation. So the first part is that we have two users. We have user 1 and user 2. Each of them, they have large piece of information which is divided into three parts. User 1 has 3 segments, 1, 2, and 3. User 2 has 3 segments, 4, 5, and 6. So if we were to facilitate the sharing of a physical medium amongst those two users without using multiplexing, what will be the order of these segments on the physical medium? Okay? So just try to access on your cell phones and try to have a discussion for 1 minute before we get to that.
Activity number 6.
Activity number 6, part 1 and 2. We'll work on both of them at the same time. Okay, okay. So very quickly, what will be the order in the first case? 1, 1, 2, 3, 4, 5, 6. Can it be 4, 5, 6, 1, 2, 3? Good, right? It depends on what? Depends on the access method. It depends who amongst these users will ask to access the shared medium first. We don't know. Maybe there is a 1 nanosecond difference between when user 1 will ask to access the medium and when user 2 asks to access the medium. But once we give access to that user, we don't do any mixing. We don't do any multiplexing. All the messages for user 1 have to be transferred first before user 2. Is this really efficient? No. Because if one user gains access to the medium, the other one is waiting forever, and he or she is starving. He wants to access the medium, and he cannot. Okay. In the next case, what would be the sequence? 1, 4, 2, 5, 3, 6. Can it be 1, 2, 4, 5, and then 3, 6? It could, depending on how small the segment is. But at least there is some kind of mixing. There is some kind of mixing, okay? So sometimes the protocol may be intelligent enough to give a part of the shared medium to different users, and sometimes, guess what? Sometimes it's not even equal. So it could be like 1, 2, quality of service, bravo Ali, 4, and then 3, and something like that. So in that case, user 1 has slightly higher quality or higher priority compared to user 2.
Is there a use for segmentation in the first case and use for case?
Use for ASDAC segmentation without multiplexing? There has to be some kind of multiplexing. You cannot, unless your information is very small in nature. If you need security or stability in the network, in all cases you need some kind of multiplexing. Even if you have security. Security will do what? Security will put some encryption inside the data. Here we're not talking about how the data is encrypted or not encrypted. Here we're talking about adding header, encapsulating this data to facilitate the transmission of this data. So whether the data itself is encrypted or not encrypted, it's not our job here, okay?
If you prioritize one user over the other, is
right.
it also called multiplexing?
Yes, it's still multiplexing because I'm still doing some kind of a mixing between the traffic, but it's not equal. So you can say it's multiplexing, but it's not equal. And as we said, assigning or sharing the medium in an unfair way sometimes is referred to as quality of service. It's like we discriminate between users depending on how much this user pays or something like this. Okay. Okay. The other activity here is a little bit tricky, and it talks about decapsulation. So we have, as you can see on the activity, we have a frame. So from the sender side, we have a frame. We have a frame which is structured as frame header, network header, transport layer header, and data, and then trailer, right? And this header and this whole frame gets sent over the physical layer as a bits. And in fact, these bits will be transferred over the medium as digital signal, right? Okay, so it arrives to the receiver. So now we need to know the structure of the message at the receiver side after we do decapsulation at every level. Okay, we need to know the structure of the message. How does it look like? All right? So just remember that the network access layer here is divided into two parts. So we have two levels for the network access layer. Why? Because we have physical and data link layer, right? So what will arrive first at the very bottom? So we start bottom up. So what will be the physical formation of this data? And how does it evolve when we go up This is the process of decapsulation, right? So we need to show the structure of the message at every level. This is very important. Okay, so very quickly, just 1 minute, just start the recording again. So what will be the form in the first level? What will the data look like? Bits, bravo عليك. So there will be like 1, 1, 0, 0, and so on. So that the same bits that we have received, assuming that there is no error. Yeah, assuming and everything arrives correctly, and that's it. Okay. So the next level, what will look like? What will it look like? A frame which contains what? So frame header, frame trailer, and no, I will not see anything inside. It's just, for me, it's data. For me, in the network access layer, I will not be able to read the network header. I don't know that this is the network header. It's everything else is just a closed box for me. It's everything inside that box. I don't know what that is. I don't know what's inside the box. In the network access layer, I don't know what's inside the box. Okay? So virtually, in that box, there is what you have just said. But for me, in the network access layer, I don't see that. Okay? Okay, then this data part, اللي هي خلاص the frame header and frame trailer have been extracted and thrown away. خلاص, I get whatever information out of them, and then I throw them away. And I send it up to the network layer. The network layer will divide the closed box into what? Network header. أيوة برافو. And date. I don't see anything else. Okay? And then the data part in the transport layer will be transport header and date. And then this data is the actual email data. Imagine that here the source wants to send an email data. So at the last level, I have the email data. Or maybe part of the email, because this is segment. Now here we're talking about one segment all the way. It could be, the email could be divided into multiple segments. Okay? So this is the process of decapsulation. That's a good question. On the receiver side, the application itself will get all these pieces of data, and then in each piece it will tell you that this is part 1 of this information, part 2, part 3. That's why we said that we have to add some overhead which tells us the sequence of these segments in the original message. And maybe one of these segments is lost, in which case I will have to send back a negative acknowledgement, or somehow I wait forever and the sender will figure out through timeout that this segment did not arrive correctly. In which case, the source will send it again. But we'll send one segment as opposed to the whole message. Okay? Right. Okay, so the last part in this chapter talks about the difference between the physical address and the logical address. And as we said, the physical address is the actual name of that person and should never change. Whereas the logical address may actually change depending on the location. And it tells us some information how to get to that person. Okay? So in the first part of that activity, talks about a scenario where PC1, which is the client, wants to communicate with an FTP server. Okay? On the same LAN. On the same LAN, which means that I can directly and physically access the FTP server directly. Okay? So what will be the physical addresses for both destination and source, and logical addresses for both destination and source? 1 minute. Okay. 1 minute for this one, before we get to the other case where we need to communicate on a remote network. So PC1 needs to communicate with the FTP server, which is on the same LAN. So a question came up, which is a very nice question. How does PC1 actually know that this FTP server is on the same LAN? And if it's on the same LAN, shouldn't the IP address be exactly the same?
No.
Of course, it should never be the same, because the IP address should always be unique. It may change from one location to another, but it should always be unique. Okay? So PC1 now figures out that it needs the physical address of the direct FTP server, because it knows that the FTP server is on the same LAN. How? Well, if you put the IP address of the of PC1, which is 192.168.1.110, and you set and you put the IP address of the FTP server, which is 192.168.1.9, you see that the only difference in the IP address is the last part. So somehow PC1 figures out that because of this similarity in the network part, that this host or this FTP server exists on the same LAN. So in that case, it figures out that it needs to know the physical address of the direct FTP server. Okay? The MAC address of the direct FTP server. Okay? So what happens if it doesn't know the physical address?
It needs to send a message.
Okay, so now I am in a class and I figure out that the person I want to talk to, he or she exists in that class somehow. Okay, now I know it. But I don't know which person. So I will announce. I will say, I will send what we call ARP requests. It's called ARP. ARP is the address resolution protocol. We'll talk about the details of that protocol in the next chapter. So ARP request is sent as a broadcast. I will say, please, who has the physical address of that IP address? Okay?
This is to the whole device on the LAN.
On the LAN, yes. Broadcast on the LAN, not on the internet. I will send broadcast on the LAN.
From what part of the IP can you tell the country? Can you tell the country from the first 3 numbers of the IP?
Usually from the network part, which in that case it's 3 parts. It could be 2 parts, it could be 3 parts. We'll talk about this on the left, yes. On the left-hand side, if it's similar, like 2 bytes, it has some indication. And it depends how large your network is. It could be like 2 parts or 3 parts. We'll talk about the details of this. Okay? But somehow PC1 will figure out from the similarity, from the large similarity in the IP address, it knows that it's on the same LAN. So it needs to know the physical address of this. If it doesn't know it, it will send a broadcast ARP request to everyone, to ask everyone who has the physical address of that IP address. And in that case, FTP server will respond back by saying, okay, I have this physical address. And then PC1 will communicate to that FTP server using the frame structure. So this activity assumes that we already know the physical address and the logical address of that FTP server. So what will be the destination physical address? C's, all C's. Physical address. Physical.
Physical is the
All C's.
destination.
Yes, destination.
The
C's. Okay. And the source physical address, that's A's. Okay, what is the source logical address?
The one that ends with 110.
أيوة بالضبط. Ends with 110. And what will be the destination is 9. Okay, so that's the first case. Power does not work here. The power is not working. The second and last case talks about if that remote host exists on a remote LAN, not on the same LAN. First, how does PC1 figure out that this FTP, or in that case it's a web server, how does PC1 figures out that the web server exists on a different LAN? Again, by comparing the IP address. So if you put the 2 IP addresses on top of each other, You have the IP address of the source, which is 192.168.1.110. Okay, and the IP address of the remote destination is a 172.16.1.99. Of course, they are not similar at all, right? So they are quite different. In which case, PC1 will figure out that this host or this server exists on a different remote LAN. So in that case, I don't need to know the physical address of this because I know that I cannot deliver any package to that person directly. I need to use some intermediate person or some service, some mail service or something like this. For us, this is the router. Okay? So in that case, I don't need the physical address of the ultimate web server. I need the physical address of the default gateway, which is the first termination of this LAN, which is the router interface that terminates this LAN. So, question now. How do I figure out the IP address of the default gateway? Because why do I need it? Why do I need the logical address of the default gateway? Because I need the physical address of that to send the ARP request to ask for the physical address of that particular IP address, right? So how would I know the IP address of the default gateway? From? لا مفيش FTP. There's no FTP server here.
It's the same as my device.
It's on the same LAN, but it's different. It doesn't have the same IP address.
I have to ask it.
You just send a broadcast message to figure out where the gateway is.
Something to the default gateway.
Yes. So it doesn't send a broadcast. If you have ever looked at the TCP/IP settings inside your operating system, you will see three pieces of information. You will see the IP address of your host, the subnet mask, we'll talk about the subnet mask, and the default gateway. It's already set up inside your workstation. So the problem is that we are not configuring these settings manually. What happens is that now we are luxurious enough to have what we call DHCP server that assigns these addresses and everything dynamically. Okay, so we don't get to actually set these values manually, so we don't see it. However, every host, once you connect on the network, the DHCP servers should give you three things: your IP address, your subnet mask, and the default gateway IP address. It has to be set up on every machine that's connected to the network. If you don't have this default gateway, you can never communicate to the outside world. Okay, so the default gateway IP address is already given. You don't need to send a broadcast to get the IP address of the default gateway. Okay, so the ARP request in that case will be, give me the physical address of the logical address of the default gateway, which is, in that case, 192.168.1.1. Okay, so in that case, the default gateway will respond back by giving you the physical address, which is all ones. Okay, so now PC1 has the physical address of the logical of the default gateway, and it has the logical address of the web server. So now, what will be the four addresses in this frame structure? Just think a little bit, and then we'll. So what is the answer? So destination physical address? All ones, right? Which is the physical address of the default gateway. The source, what is the source physical address? All A's. What is the source logical address? It's 192.168.1.110. What is the destination logical address? 172, huh? Not the logical address of the default gateway. Right? Remember that. Logical address does not change. Physical address changes from one LAN to another. So the destination logical address is 172.whatever.95. Okay?